first speaker is Misha Shifman, who will tell us about peculiarities of the supersymmetric domain walls.
Okay, thank you. Thank you, Igor, for inviting me. And I will discuss the topic mostly, but not exclusively, of the multiplicity of the degenerate in energy domain walls in super Young Mills and in supersymmetric QCD. This is, of course, a very old question. It bothered me. There was some kind of sort of mismatch. It bothered me from the late 1990s. I returned to this issue several times, in particular in early 2000 with Arkady Weinstein and Adam Ritz. We published a couple of work which only could be compared with the Acharya and Wafa results, and on the surface of it, the prediction was the same, but it wasn't. Well, essentially. Then there was some work carried out in between. In the year about 2020, I had quite a number of discussions with Zohar. We came to some intermediate compromise, of which I will tell you towards the end of my talk, and it seems to me that finally we understand now everything I mean by we. This is Shi Qian, it's our student, Eugene Ivlev is postdoc from St. Petersburg, and myself, after a few months of work. So here is a very brief plan. I will tell you about the history of the issue and why it was a little bit confusing. The point is, there is a joke when an old merchant is asked to teach his very small, very young grandson how to count. So the grand comes and asks him, please teach me how to count. And then he asks, there are two systems of counting. The first one is if you sell, and the second one is if you buy. So the situation here is a little bit, turns out to be a little bit similar, because before we count the domain walls, we should realize what kind of counting is taking place. And finally, the last question is about the phase transition. Very brief historical review. I'm talking about SUN super Young Mills. Later we will add some matter fields, but only with masses, without interaction superpotentials. In this series, we know that Witten index is equal to n for SUN gauge group. And so there are n degenerate vector, which are labeled by the value of the Biglie-Wiener condensate. Biglie-Wiener condensate is defined as proportional to square root of 1. So there are n different values. They sit around the circle, equidistant, and because all vacuum are at zero energy, of course there are configurations which interpolate them, and then these are what is called four-dimensional domain walls. They are 1 plus 2-dimensional objects of codimension 1. And we can consider a large variety. Of course, if we choose the initial vacuum and the final vacuum, there are a number of apparently distinct walls, but they are all related to each other. That's not what is interesting. What is interesting is fixed initial vacuum and the final vacuum, and consider what happens with domain walls in this situation. The wall interpolating between neighboring vacua is called elementary or minimal wall, but of course you can interpolate not necessarily between elementary transition, but also consider from vacuum n to vacuum n plus k. So such walls are called k walls. All of them are BPS saturated. The central charge in the commutator of Q alpha, Q beta has been discovered by Dwali and myself in 1996. It's anomalous. If you see, because of pi, you see that it's an anomaly. It is hidden in the supermultiplet of supercurrents, but usually people used to ignore it. But if you honestly write all components of this supermultiplet and anti-commute them, you will see that this is hidden there. And because the values of vacuum expectation values of the Bragg-Levine condensate in vacuum N have been already, even before in the 1980s, they were calculated exactly using the instanton formalism. You take the difference and you have the, well, originally it was central charge. It's not quite correct because you see it doesn't commute with the central charge, doesn't commute. You see it has indices. It doesn't commute with rotation, Lorentz rotation. So Nati suggested to call it brain charge, which has some meaning in this particular case because this domain, BPS saturated domain walls in Young-Mills were shown to be fully analogous to the brains of the strings theory almost immediately, a year later by Ed Witten. Huh? You can switch. Yeah, I can switch. No. Okay. So our task will be counting multiplicity of the general walls at given value of k and n. Of course, they are all degenerate because they interpolate between a certain pair of the vacua. There is the fixed central charge, and if they are BPS saturated, which we believe it is, these walls are all degenerate in itself. So I will come to this plot a little bit later. And now I go back to 1997 when we discovered, almost accidentally, we worked at that time not in pure super Young-Mills, but with the problem which was due to Affleck, Dine, Zeiberg, SU2 theory, gauge SU2 theory with one flavor of quarks with mass, which can be varied from very small to very large. This problem is characterized only by one modulus. You see, index alpha is color index, and index F is subflavor index. It's not flavor. We have two flavors, one flavor, but each of them is built of two subflavors because we need to, for this theory, we need to introduce two chiral superfields, Q1 and Q2. This modulus is automatically color singlet and flavor singlet. So when we started, if M, this parameter M0 is the mass term of this scalar field, scalar superfield, and to begin with, we begin with very small value of M0. By the way, in this form with the bare mass, this term in the Lagrangian doesn't change as we run from UV to infrared, to extreme infrared. So we can choose M0 small, then and include also the non-perturbative. This is perturbative contribution. There is a non-perturbative contribution to the superpotential, which is up to a number fixed by generalized R symmetry of the model. It only can have the form lambda to the fifth divided by M, with no corrections to it. So if you add these two terms, then you will see without the mass term, superpotential will produce a potential which pushes M to infinity. So no stable vacuum, but mass term, if it is small, stabilizes the theory at large but finite value of M. There is vacuum, and then if you add these two terms together, you will see that there are two vacua in the combined superpotential. And so there is a domain wall. At small m, when at small m naught, when m large is very large in the vacuum, this is a weakly coupled, arbitrarily weakly coupled theory. And you can do all calculations in quasi-classics. And that's what we did. This is one vacuum. This is the modulus M. One vacuum, another vacuum. You can choose your parameters in such a way that these points are real, positive and negative. And then there is an BPS equation, and you find the solution, and you see at the classical level, there are two distinct solutions. In one solution, M goes from a vacuum to another vacuum in the upper complex half plane, and in the second solution, it does the very same curve in the down complex subplane. And in fact, there is a symmetry, discrete symmetry, with reflection to M into M dagger. This in M, if you write the same graph for M dagger, you get this solution. Okay, so from this simple observation, we concluded that there is a non-trivial multiplicity in domain walls. Degenerate domain walls. The next step, okay, I'll come to this later. The next step was made a few years later by Acharya and Vafa, who considered the same wall construction, but not in the field theory, but exclusively in string brane theory, where you have branes which wrap around something and strings, and they come to the generic formula for arbitrary n and arbitrary k, that the number of walls is given by a binomial coefficient. Okay. They worked in pure Young-Mills theory, super Young-Mills theory, no matter fields. Okay. And so they were, then there was a paper 2 years later by Ritz, Arkady, myself. In fact, there were 2 joint papers and 1 paper by Ritz, who did the same using the same contribution, using, again, adding, let's say, some number of matter fields, and the formula, which is then at weak coupling, these matter fields show up at the whole volume of the string as the Grassmannian model. And the Witten index for the Grassmannian model, this is the Grassmannian model, Witten index is exactly the same. So on the surface of it, these expressions coincided, but there was a big but. Because the domain wall detected in SQCD with matter fields could have a two-wall junction. What does it mean, a two-wall junction? You have 2 degenerate walls, like this and this. Each of them has the same tension, but they are supposed to be different. And if you put them together, you have a junction in the middle. This is obvious in this approach of Ritz because we are just working with Grassmann sigma model, and there are a number of vacua, and there are kinks or lines, if you wish, which can separate one wall from another, and you can say it explicitly. However, as for the Acharya-Witten, people very quickly realized that it's not the case. That what happens with the Acharya and Witten, Acharya and Vafa, is that on the domain wall, on the wall sheet of the domain wall, there appears a topological quantum field theory, Chern-Simons, and it's at a certain Chern-Simons for the gauge group UK at a certain level related to N. And of course, locally, formally you have a large number of different strings, but they differ only by topology. So only if you study the string as a whole, if you have experiment that fills the topology of the string, that is to say how R4 is being compactified, these numbers will be different, but locally all of them, under any local experiment, they are identical. So you cannot have a domain line between them, a junction, because junction between what and what. Locally, there is no difference between them. So this was a puzzle of how the counting, what do we count? Do we count the same object or different object, and how the one goes to another if we play with the mass of the gauge field. So let me say what new elements I'm going to add. All tools were already in place in early days, but it's only the combination of them in application to this problem which seemingly produces the answer to this puzzle. First of all, what do we need? We need instanton localization to explain ADS. We need and use Unsal's adiabatic continuity. And we also we introduce arbitrary number of flavors in arbitrary SUN and play with these both parameters. And then we see what happens and can make a statement about the phase transition from one picture to another. Okay, now about localization. This was localization in SQCD, an SU2 SQCD with one flavor was detected in 1985 by Novikov, Arkady, Weinstein, Zakharov, and myself. It is not a widely known statement, but it was the first example of self-localization of the instanton. What does it mean? It means if you calculate the instanton measure, there is some kind of very strange situation. Here is the full instanton measure in the theory with one flavor, SU2 theory with one flavor. You see, without flavors in pure Young-Mills, you get only translational modulus and super translational modulus. Also, you get a super conformal modulus. So you don't have this modulus, theta null, which is related to the zero mode of the fermion field, of the matter field. If you introduce this modulus additionally, you will see that you can find combinations of the other modulus which are invariant under super translations. Okay, one of these combinations which we need is the instanton size. It's the normal non-supersymmetric instanton size is rho squared by division into this combination, which only appears if matter is included. It becomes invariant under supertransformation. Now, in terms of this, this is the exact one instanton measure. Here, every power of everything is important. You see, it's expressed in terms of a function of rho invariant. This is the weight function in rho. The integral in rho goes d rho squared over rho squared. So for fixed beta and theta, it seems that you can multiply by this factor the numerator and denominator, and then it will be d rho squared invariant, rho invariant squared. So all beta and theta are now hidden in rho invariant. You first integrate over rho invariant, and then you integrate over beta and theta, but there are no more explicit beta and theta, so this is formally zero. So if you act naively, you say that one instanton contribution upon the change of variables is zero. Now, this is a loophole. This zero occurs because of singularity. You have to be careful. This expression at singular at rho equal to zero. We don't think that rho can be infinity because of this damping factor, but at rho equal to zero, we have to be more careful. So what can you do? You can integrate in a different order. First, you integrate over d beta bar, d theta bar, and then you integrate over rho. So here I take this part of the measure, depending on arbitrary function of rho invariant, and I first integrate over rho or over beta and theta through expanding back rho invariant, and then I integrate over rho, and I see that the first integration produces a delta function of rho invariant. Here the last line explains how this beta function emerges, delta function emerges. So you see that the measure is absolutely local. It saturates at rho equal to zero. So instanton of the zero size produces the entire instanton-induced superpotential. Okay, What does it mean? What does it mean? It means that this term, instanton produced term, is independent of any scale. You see, it could have been inserted in the classical superpotential from the very beginning as a bare term. Since it's saturated by zero size instanton, it's not the result of evolution. You don't have to integrate out fields, matter fields, to obtain this term only at large M naught. This term is valid for any value M naught and any value of M. What does it mean in practical terms? It means normally at that time people would say that this consideration of the domain wall was valid only at small m naught, because at small m naught M is large. M is large, the gauge bosons are heavy, so you can integrate gauge bosons completely, and what remains is just the M moduli, which is very weakly dependent on anything because parameter M naught is small, and then we can solve the problem of the instanton solution with two walls. Now, when we know that instanton measure is saturated at 0 rho, we can say that forget about integrating out gauge bosons, let them fly as is, but this superpotential for the M modulus is still generated, and you can consider it even if M is large. Then, of course, what happens when M becomes as large? The size of this contour shrinks, but there are still two of them. And you can locally distinguish this. Let me explain what happens. I'm sorry. Okay, what happens with the structure of the domain wall as I change M naught? This M naught. If M naught is very small, and lambda QCD, SQCD is very large compared to M naught, then domain wall has the following structure. Very narrow core made from glue, and the huge tail to the right and to the left made of very light matter fields. You see here the thickness is 1 over M. The thickness of the blue part is 1 over lambda. Now, if you make M large, it's the other way around. Now the glue is spread by the distance 1 over lambda, and there is only very thin core, which width is 1 over M. But if we have energy, but it's still a locally distinguishable situation for any M. Here it's just because of the existence of the sigma model on the wall sheet. Here, of course, it's not the case, but you can do experiment. If you have a local beam of particles, you throw it, and the energy of order of M is large, you throw it, and then you detect backward scattering, and you can say what is the internal structure of this matter core. So the counting becomes, although technically may be challenging, but these type of strings are locally distinguishable. Now, the type of strings, now if you get rid of matter fields, if you go to M going to infinity, I argue that there is no phase transition other than at m equal infinity, you return to pure Young-Mills with a Cheryav-Waffa Chern-Simon solution on the Wooled sheet. And then, although the number is the same, the formula the same, but you cannot see it locally. Okay, I understand that I have no time. Let me only happens now another tool which I want to use. I have very little time. It's about adding unsal circle, that is to say, to pass from R4 to R3 plus S1. When you can, for fixed circumference cell, you see that in pure Young-Mills there appear, in addition to the quark moduli, which I discussed previously, there appear the so-called monopole moduli, which I denoted by capital Y. The superfield in 3 dimensions, real superfield is built, rho is just a vector, okay? It's made of simple weights, but the dynamical field is sigma plus I gamma. Sigma is what happens to one of the components of the full potential A mu. If you take the component which looks in the compactified direction, in direction of S1. Okay, and gamma is the dual Polyakov photon field, which plays the role similar to a phase because it's a compact field. Okay, so there is this superfield, and on its basis, this goes here. On this basis, you build these moduli, which are called magnetic moduli. And then you can see, you can play now also, can count with the help of this moduli the number of domain walls, even in pure Young-Mills. When L goes to infinity, this moduli disappear, but if they are not infinite, L is not infinite, but fixed, then they exist, and you get a very similar, for instance, SU2, you get in terms of this Y exactly the same potential as Affleck, Dine, and Zyberg. And so you can, literally repeat the calculation with Affleck, Dine, and Zyberg and see there are two walls. For finite L, they are distinguished locally, but as L go, yeah, I'm finishing. I'm sorry.
That wasn't the intent.
I'm sorry.
But it would be nice because.
Yeah, I'm already 5 minutes, 6 minutes late. So the difference between various domain walls, visible and locally distinguishable and not globally distinguishable, is similar to what we considered in SU2. You can pick up one of the moduli, some of the moduli in this picture. Let's say here we have SU2 theory, or some theory. We have vacuum here, another vacuum here, and then some moduli. If you want to build a domain wall, you let some moduli travel anti-clockwise and other moduli travel clockwise. And this can be a mixture of moduli. Some of them can be quark moduli, and others can be monopole moduli at finite L. And but you just this is a simple combinatorics. You introduce J, a number of flavor quark moduli winding clockwise. Clockwise means like this. And then you split all moduli into flavor and monopole moduli and calculate separately the combinatoric number for, because J can change in this interval. And then you get the sum of the following product, and it sums up exactly to the Acharya-Vafa formula. But here you count all of them. So all domain walls are now split into two parts. For some parts, it's when the moduli building domain walls are monopole walls. In the limit of large L, they become locally indistinguishable, only topologically distinguishable. But there are some walls where you restructure all the flavor moduli or quark moduli, they will be locally distinguishable. And for them, two-wall junction exists. But if you combine these two numbers of different nature, the walls with junctions and the walls without junction, you get the full formula of Acharya-Vafa, so it looks like a certain kind of a, not Witten, but some kind of index exists. It was suggested to me yesterday by Thomas Dumitrescu. Okay, that's my last picture. It's about the phase diagram. The phase diagram, you know, when we discussed with Zohar, we have only line, not the plane by the line, because we didn't study the dependence on the second parameter, which is beta 1 over L. And L is the Unsal circumference. Now we have the plane, and we have two strips in the plane, this greenish and this bluish. In these two strips, there is a weak coupling, and we know everything. So that's the plane where we want to go. You see, L is very large, beta is very small. So the original model in R on R4 corresponds to this line. And let us assume that there is a point of the phase transition on this line downstairs where you know what it happens, that all domain walls become locally identical. Then here, of course, they are locally distinguishable. Here they become locally identical, so it's a phase transition. And then there are four options for this line of the phase transition. Now we can quickly exclude all of these options, because let's say take option 1, then you would be able to see a phase transition on this greenish strip. I'm finishing. I'm sorry. And we don't see it. Line number 2, the same story. Line number 3 adds this line where all quark masses are infinite, and therefore adiabatic continuity works, and then there is no this transition. So what remains is only to say, we are forced to say that there is no such point here, and the points of phase transition only at m equal infinity. Not at large m, but at m equal infinity. And my final sentence is that it was assumed, here you see m2 points. Recently, there is some discussions in the literature that there is a certain phenomenon that if you you have that even you break at large you break some, so let's say center symmetry explicitly. At low energies, in a low energy limit, they can emerge the exact symmetry of the type of the center symmetry, and then there will be confinement here at low energies. I claim, or we claim, that this point doesn't exist, only both of them can be only here. That's because no matter how large is the heavy quark, it's still dynamical if your contour, you have to take a very large contour to see area law or perimeter law. The contour should be large in the time direction at least as 1 over m, and then it's exponential, I'm sorry, in the space dimension. It has to have be so large that it carries together cumulatively 2m of energy, which implies very large contour. And in time direction, it is exponentially large because you have to wait a tunneling in order, quasi-classical tunneling in order to produce a pair of heavy quark antiquark, which will screen the probe charges. So the conclusion is that both these points lie at m equal infinity. Thank you very much.
Thank you very much, Misha. Yeah, Ofer has one.
So what happens to the two-wall junction when m goes to infinity? Does its energy density go to infinity?
When m equal to infinity, let's say in the theory with one flavor, like SO2 with one flavor, okay? For finite masses, you can distinguish the cores of these walls with enough energy, and they are locally distinguishable. Now, when m goes to infinity, these courses shrink into point of zero thickness, and they become only topologically distinguishable, like in pure Young mills.
So the energy of the junction goes to zero in this limit.
Junction disappears, yeah. Because locally they are the same string. How can you make a junction between them?
Okay, well, in view of the time, let's thank Misha again.